Hi everyone, welcome to uh, this lecture on energy efficiency and renewable energy under this broad topic that you're covering in this course, which is sustainable strategies, perspectives from India. So the first question that comes to my mind is why are we talking about sustainable strategies? Now, as we look at the world around us, we see that there are several ways in which we are not being sustainable. And what really sustainable is, sustainable really would mean that we consume products and services in a manner that is sufficient to meet our needs, but it does not compromise the needs of the future generations. So, are we? I mean, we do see that we are not doing sustainable. We are not doing sustainable consumption in several areas around us in many of the activities that we are doing. And one of the activities in which we are not being sustainable is the way we use energy. And energy efficiency and renewable energy are two strategies, not only in India but internationally all over the world, to address the the challenge of sustainability in energy use. So, going into the flow of today's lecture, I will begin by elaborating a bit on the problem and what are the existing solutions that we are using. Then we look at how are we measuring the impact of these solutions. And then we come to the very uh, specific topic on how can we best measure the effect of energy efficiency and renewable energy on one of the goals of sustainability, which is to address climate change. So let's begin with the energy problem, if I may call this as an energy problem, and we begin with some numbers. So the numbers are for India, and within the bracket, I've kept some numbers for the world to get a comparative sense of these metrics. So the first is per capita energy consumption, and many of us have heard this a lot that in India the per capita energy consumption is very low. So ours is around zero point 0.6 tons of oil equivalent per capita, and the world average is 2 tons of oil equivalent per capita. And if we look at the developed nations, it is almost 10 times that of India, 10 to 12 times that of India. So what is the problem with this? What the problem with this is, this per capita energy consumption does not reflect the energy consumption which is used by high income group. This per capita energy consumption, having such low per capita energy consumption, is a reflection of many households which do not have access to energy, clean energy meaning. So when we calculate per capita energy consumption, we look only at the commercial energy sources. So what are the commercial energy sources? It is coal, oil, natural gas, electricity. There's another category of energy sources, which is non-commercial energy source, which is biomass, cow dung, firewood, and so on. So India is still even in 2018, we are still we are deriving 21% of our primary energy supply from non-commercial energy sources. And this energy consumption is not getting captured in per capita energy consumption. Not that it will increase the per capita energy consumption significantly, because or it will increase the benefits of energy access Because what happens with the burning of biomass, what happens with the use of non-commercial energy sources is that it is associated uh, with pollution, with indoor air pollution. So when a household burns firewood or uh, or uh, or coal, even coal inside their small house, in the small kitchen, it releases several pollutants. So these pollutants can range from carbon monoxide to nitrogen oxide to sulfur dioxide, particulate matters, which have severe impact on the respiratory system of the household. So India faces this energy access challenge. And energy access meaning, if I use that coal in the power plant to generate electricity, and that electricity is used in the house to cook for cooking, it is clean at the point of use, though it is still not clean when we look, because that coal which has been burnt in the power plant has emitted all of those pollutants. It is easier to manage it there, but the situation is still there. Okay, so the energy access challenge is the first energy problem for India. And when we look at the United Nations Sustainable Development Goals, the goal on energy is essentially focuses on energy access, of course, on energy efficiency and renewable energy as well. But one of few of the indicators are on energy access. The second problem starts to come in when we see what constitutes our commercial primary energy supply, and we find that 95% of that energy is from fossil fuels. If we break that down into the three fossil fuels that the world and India uses, coal has more than half of the share. Oil is mostly imported. Natural gas is also a significant part is imported. Coal is produced, some of the coal is produced domestically and some of it is imported. So two challenge: one, this fossil fuel; two, a lot of it is being imported. If you look at the similar number for world, it is around 89%. So the situation is not very different in terms of heavy dependence on fossil fuel. When we look at the share of renewable energy in India, so large hydro is around 2%, and other small RE, which we are now trying to push in the RE goals that we have, it is the solar and wind energy sources. These are also known as the new and renewable energy sources. So hydro is an established energy source, and in the middle you see the nuclear, which has radioactive wastes, but it does not have any local pollution problem, and it does not have any carbon dioxide or climate change related problem, which we'll come to in the next slide. If you look at the similar number for the world, it's not substantively different. Yes, nuclear share is a bit higher. RE is not significantly higher when you compare it with India. So the key challenge in our energy system, if we look at the key challenge in our energy system, it is the dependency on fossil fuel sources. So one problem with the fossil fuel sources, which was realized in 1970s with the oil crisis, is that it affects the national security. Now, these energy sources, when you look at oil, it is not equally distributed. If you look at coal, it is not equally distributed across the world. And if it is not equally distributed across the world, that means countries are dependent on imports to meet their energy needs. And when we look at the distribution of energy sources within the country, then also we see that the usage is also is also unequal. There is inequality in the way energy is used across different across different states and different income groups in these states. And because of which we see that there is poor access to clean energy sources. So when I say clean energy source, we have to keep this in mind that when we look at our goals, sustainable development goals, we say clean energy source is a source which does not emit pollution at the point of combustion. So like LPG or PNG, which the liquefied petroleum gas or the piped natural gas or the compressed natural gas CNG, these are considered clean energy sources when we think of the energy access as a problem. But these this is also a fossil fuel. It is not associated with significant amount of air pollution. But burning of any fossil fuel is a problem because they cause climate change. Until a long time, I think if I look back, until around 1990s, the bigger problem was with the import dependency, with access, with finiteness of fossil fuel sources. But as time progressed, and from 1990 onwards, we've realized that even if we leave some of the fossil fuels into the ground, we still can have a major problem due to climate change. So how is climate change related to energy use? Any fossil fuel, when burnt, releases carbon dioxide. When carbon dioxide is released in the atmosphere, but carbon dioxide should be good because carbon dioxide is good for us. So carbon dioxide is indeed good for us, but too much of carbon dioxide is not good for us. So why is carbon dioxide good? Because it is a greenhouse gas, and what it does is it maintains a livable temperature on the planet. But if the concentration increase, if there is more of carbon dioxide being pumped into the atmosphere, there is more of the carbon dioxide remaining in the atmosphere, it means that the greenhouse effect is increasing, or there is an enhanced greenhouse effect, which results in increasing the temperature of the earth. Now, when the earth's temperature increases, which is global warming, what it does is it changes the entire climatic system. It changes the way our ice sheets are, the way our sea levels are. It changes the way air currents flow. It changes the way ocean currents flow. It changes the way cyclone formations it changes the frequency with which cyclone formations take place. It changes the frequency of the rainfall, the intensity and frequency of rainfall. Okay, so it changes a large number of changes. It brings in large number of changes in the climatic system. So, as I said, finiteness of fossil energy sources is not really a problem anymore, because we cannot afford to burn more and more of these fossil fuels, because they are associated with emission of carbon dioxide. So the immediate solution, or the only solution to energy and climate concerns, is to reduce our dependence on fossil fuels. Now, when we look, as we saw the numbers, such heavy dependence on fossil fuels, and now we are saying we reduce dependence on fossil fuels. So what would it take for this to happen? Is it possible? First question that you would ask is it possible to wean off fossil fuels? So can we live without fossil fuels? So I'm not going to answer that question here, but what I'm going to do is I'm going to look at two of the strategies which have been found to be two important ways of meeting this objective. Whether or not we are able to meet that objective, we'll not cover in this, but that's an interesting area to see, because if we don't, then we are doing something which is irreversible. So we have heard of climate change being irreversible. So we're not going to whether we are what do we know about whether we are able to do it or not, but we are going to look at two of the ways which have been thought to be the best approach to reduce our dependence on fossil fuels. So it's not been straightforward. It's not been straightforward to shift from fossil fuel to non-fossil fuel. And obviously, because there have been several market barriers and market failures. And one of the most evident and clear failure of the market is to internalize the cost of pollution from burning of fossil fuels. Though that is true for many products, for many products, we do not internalize the cost of, say, disposing the product. That's true for many products, but focusing on use of energy, we have not internalized the cost of pollution due to burning of fossil fuels. What would it take? What would it do if we wanted to internalize the cost of pollution from fossil fuel? The prices of the fossil fuels will go up. Now that has been not used as a policy or as a policy instrument to meet this objective. And you'd understand that, increasing prices of fossil fuels, what sort of effect it can cause on economy, or the policymakers may think what kind of effect it may cause on economy. So best not to tinker with that. Although if you are interested, you should look at the literature on carbon tax to get a sense of how we are trying to bring a pricing instrument to meet this challenge of reducing our emissions from emissions of carbon dioxide. So when we look at the existing policies to promote energy efficiency and renewable energy as a means to reduce our dependence on fossil fuel, we'll find that these are the second best instruments. The first best instrument is the pricing instrument, which is either, say, you put a tax, or you put you give targets to companies and then allow companies to trade their emission reductions with other companies. But we don't see much of that happening. So we are relying on the second best solutions. So the kind of interventions that we see around us to promote energy efficiency and renewable energy essentially includes regulations, market-based instruments, combination of regulations and market-based instruments, and fiscal instruments. So when we look at, say, India's approach to renewable energy, now in India, interestingly, for renewable energy, there is no legislation. There are discussion that, so for each of these points, there are discussion in different acts, but there is no standalone legislation for renewable energy. Okay, so we look at some of the mechanisms which have been used in the country, in India, and this is a similar approach has been used worldwide as well. But we look at some of the approaches. Okay. Now, the simplest is the feed-in tariff. So feed-in tariff is a guaranteed above market price for production of electricity using renewable energy. Renewable energy, generating electricity from renewable energy is expensive, more expensive than that of coal. When we look at more recent numbers, it reflects the other way, the story other way. But there also there are certain problems in that, the way the competitive bidding process has taken place. But feed-in tariff is straightforward. If there is a renewable energy source which is generating electricity at a cost above than that of uh, the the other or mainly coal-based electricity generation, then the producer is guaranteed an above market price for production of that electricity. And they have fixed, and the government fixes how much would be the feed-in tariff for electricity generated from wind or solar and so on. Another mechanism which was used earlier in the 1990s, which led to development of wind generation and the wind installed capacity from wind and generation, is the accelerated depreciation. This is simply to give some tax benefits to the investor by allowing faster depreciation of investments in the RE project. Now, the most recent that you might have heard in the news is about the competitive bidding, in which the government decides that this is the capacity of renewable energy that I want to put in place. So I invite proposals, or invite I auction this capacity and ask for bids. Okay, I ask for bids on at what rate can they provide that electricity from that renewable energy source. So through this, we have been able to bring down the cost of generating electricity significantly. Now, there are several issues around this, but yes, this has been the widely used means to bring down electricity cost from renewable energy sources and increase the installed generation capacity in the country. Now, finally, having capacity alone is not sufficient. So we need to have generation from electricity. So there is renewable portfolio standards, wherein the distribution utility, or the company which is responsible for distributing electricity to consumers, is given a target to ensure that at least that much of percentage of electricity that it is selling should come from renewable energy. So what electricity utilities do is they have power purchase agreements with electricity generators. Now, they can choose electricity generators using generating electricity from coal, RE, and others. If they choose, if it is cheaper, they would go for coal. But if a regulation is put, no, at least certain percentage has to come from renewable energy, then they have to buy more expensive electricity, if it is expensive, from RE generators. So this is a standard that has been put. This is a regulation that mandatorily you have to buy this much electricity from renewable energy source. But along with this, the government has also introduced a market mechanism, which is known as the renewable energy certificate. So if a utility or any consumer who has been asked to procure some of the power from renewable energy, they're not able to do it. They can buy certificates from the market, and the certificates in the market come from those utilities who have been able to meet their targets and exceed their targets. So the difference between the exceeded target and meeting target, whatever is remaining, they can now sell it to the market, and those who have not been able to meet the target can buy it from the market. So this is a regulatory market-based approach that the government has adopted to promote renewable energy. Okay. Now, similarly, when we look at the approach to energy efficiency, it's been a mix of information, regulation plus market instruments, and so I would actually say it's mainly, and the final is the public procurement program. So giving information through labels. Now it can be information through appliance labels, information through building codes, information through mandatory energy audits of industries and agriculture and municipal services, information of vehicle efficiency standards, vehicle efficiency on labels. Now, the moment you make the label mandatory, it becomes a standard, because a label below certain performance value is then now not allowed to be sold in the market. So it becomes a regulation, it becomes a standard. Okay, so as of now in appliances, yes, there are standards. In transport, there are no labels, no standards. In buildings, there are no standards, there are only labels in India. In industry and agriculture, it's mainly energy audits. Okay, and in industry, there is a very interesting scheme in India which is known as the Perform, Achieve and Trade scheme. In this also, the industries which are energy intensive, they use a lot of energy, they are asked to reduce their specific energy consumption. So not energy consumption, because if they increase their production, then the energy consumption is going to increase. But energy used per unit of output is the specific energy consumption, and they're given target to reduce that. Here also, there is a scheme of certificates trading. So if I am able to exceed my target, I get certificates. And there is an industry who is not able to exceed the target. So they will to meet the compliance of reducing specific energy consumption, they can buy these certificates from the market. So a mix of so in renewable energy, we see a lot of we see some fiscal instruments and mix of regulatory and market mechanism, and in energy efficiency, we see again similar approaches. So the question now comes, okay, we're doing a lot to promote these technologies which are expected to reduce our emissions. How would energy efficiency reduce our emissions? So we are generating now the same output with lower energy. Okay, so our energy demand is going down. Our output is not changing. So this definitely has an impact. This definitely reduces our dependence on fossil fuels. It's not that our consumption is going to go down. Our consumption is still going to go up, but the rate at which the consumption goes up is going to be lower. Renewable energy is straightforward because you are replacing fossil fuels with or fossil fuels with cleaner energy source. So these two are in that way going to help meet our objective. Now the question comes: how is the impact of these two strategies? How are they reported? So when you look at renewable energy, the common way to tell about how we are improving on our renewable energy, and this is what our sustainable development goal indicator is, that what is the share of renewable energy in the primary energy supply or in electricity generation. I do not recall exactly which one it is, but it is the share of RE, and that is what we need to improve, we need to increase. And we have also heard of targets such as 175 gigatons of renewable energy, or now we're talking about even increased targets on that. So that is installed capacity. So gigawatt of installed capacity. So installed capacity, and then you look at for how many hours in a particular day, month, or year that power plant works, and then you arrive at what is the electricity that it actually generates. So if you have 100 gigawatt of RE capacity, but those generators never come in operation, they never operate, so there is no electricity that's generated from them. Or if they come in operation for 10% of the total number of hours in a year, then you can accordingly calculate what is the electricity it generates. So it's a function of the time for which they operate. And the problem with renewable energy, which has been understood, is that because the sun is shining for limited hours in a day, wind is flowing for limited hours in a day, and in a season or in a year. So the percentage of hours in which they are operating as compared to the entire year is quite low, which is known as the load factor, or plant load factor, or the capacity utilization of the power plant. But these are the standard ways of reporting the impact in terms of how much of renewable energy are we have we put in place. When you look at energy efficiency, we see it's a bit more tricky to estimate what is the energy that is saved by implementing energy efficiency measure. With PAT scheme, fortunately, it's been quite simpler because PAT scheme was implemented in industries. Industries had meters, electricity meters, or they had a clear a clear measurement of how much of the fuel is entering into the premise and how much of production is happening in that industry. So it had a clear system of measurement, field measurement, actual measurement, and hence it was relatively straightforward to measure the energy saved, and you can always calculate from energy saved how much of carbon dioxide has been abated, how much of carbon dioxide emissions has been avoided. So if this energy had not been saved, additional 31 million tons of carbon dioxide would have been emitted. And this scheme, this impact is for the first cycle of PAT scheme, which was from 2012 to 2015. There is additional saving which happened from 15 to 18, and now additional saving of I think around 6 million tons, around that number. Now, what happens with measuring energy efficiency impacts in, say, agriculture pump set? So what government does is, what distribution utilities do is they promote energy efficient pump sets for farmers. Now, if the farmer takes up that energy efficient pump, then how I would calculate the energy saved? I will look at what would have been the energy consumption if that inefficient pump would have been there, and what is the energy consumption of the new pump. A major problem with this calculation is that I have to make an assumption on how many hours does this pump work. Now, if my assumption is on a higher side, if I assume that the pump sets are used for a longer number of hours as compared to what they really are, I am overestimating the savings in energy. Similarly, if I underestimate the number of hours used, then I'm underestimating the energy saved. So this is the problem with what is also known as engineering analysis, or it's also known as engineering analysis, engineering calculations engineering method of calculating savings. So it's been found in the literature that the engineering estimates are actually overestimates of savings, actual savings. So if you do the same thing for say a premise which is metered, and you do the estimations from engineering estimate, and you do actual metering, and you look at a set many such premises, and when you aggregate them, you'll see that, I mean, researchers have found that the engineering estimates are often an overestimate of savings. There is another way of reporting the energy saved, which is to say how much of capacity, how much of capacity demand has been reduced. So, for example, in case of appliances, the government implemented an Ujala scheme, wherein the LEDs and other efficient appliances were given at lower costs, and then there was a provision that consumers can pay that additional extra a higher cost in their monthly electricity bills. So that the estimate of savings from that is in terms of reduced capacity demand. But if I want to say what is its contribution to the energy goal, or what is its contribution to the climate goal? If we look at India's energy goals, we don't have any quantified targets for our energy goal. But when we look at the climate goals, we have quantified targets. So the questions we really ask is, okay, these are good numbers that, what's the share and how much of energy we have saved from this program and that program. But can we use the aggregate values of energy and emissions to say how are we progressing in our climate goal? And that's where the rest of this lecture will focus on. So as I said, we don't have any substantive energy goal, but we do have quantitative climate goal. So we look at how our energy efficiency and renewable energy, using aggregate values of energy and emissions, how are these two strategies helping us in meeting our climate goal. Okay. So we talk about what is their contribution in reducing India's carbon intensity. Now, before going to carbon intensity, we very quickly look at what is India's climate change mitigation goal. Now, this goal is actually specified in the nationally determined contributions that every country which is party to UNFCCC has to submit under the Paris Agreement, which was agreed in 2015 and ratified in 2016. So in 2015, the NDC that India submitted had 3 quantified targets. So the first quantified target was to reduce the emissions intensity of GDP by 33 to 35% by 2030 from 2005 level. It has a renewable energy target of 40% cumulative electric power installed capacity from non-fossil fuel-based energy sources by 2030. And it has an afforestation target to create forests so that forests act as carbon sink. They absorb carbon dioxide. So we have a quantified target for afforestation. Now let us focus on the emission intensity target. Now this is emission intensity, emissions of all greenhouse gases. Okay, so greenhouse gases include carbon dioxide, methane, nitrous oxide, and fluorinated gases. But we will find that carbon dioxide is almost 70% of the total greenhouse gases in terms of CO2 equivalent. So what we do is the methane is emitted in a different quantity and carbon dioxide is emitted in a different quantity, but they need to be brought in the same unit, because when we say carbon dioxide emitted, we will say gigatons of carbon dioxide. When we say methane emitted, we will say gigatons of methane. Now carbon dioxide and methane, they cannot be added together in their physical quantities. So what is done is the equivalent of methane is calculated, and equivalent in the sense that how much of in the sense that what is the warming capacity. So global warming potential is the term which is used to calculate what is the CO2 equivalent of a given quantity of methane. So for example, one ton of methane is equal to 21 ton of carbon dioxide. So that's the conversion that's used. When you look at in the CO2 equivalent terms, carbon dioxide share is around 70%. And this is the only gas which is increasing at a much faster rate than any other gas. And that is why it becomes important to look at carbon dioxide as how we can reduce it to reduce our emissions intensity. When we see in the NDC, what are the measures, what are the ways that we are as a country we're thinking of meeting this target? We see that we're talking about efficient and cleaner technologies, renewable energy, transportation sector, energy efficiency in industries, transport, and so on. So the focus is on E and RE. And of course, reducing emission from waste and afforestation is also there. We now take our focus to CO2 emissions. So we see that total greenhouse gas emissions, a significant part is carbon dioxide, and much of that carbon dioxide is coming from energy sector. And why from energy sector? Because of the fossil fuel burning. So fossil fuel burning constitute a major share for the greenhouse gas problem. Okay, so we just look at the energy CO2 emissions. Now, what is the trends? What is the trend that we see? We see definitely an increasing trend in energy CO2 emissions. Okay, but the emissions intensity, which is CO2 emissions divided by GDP, in constant, so in real values. Okay, you remove the inflation part from it. In the real values, what is that? How is that changing? And we see that it was declining until 2005. It increased during your economic crisis, and then it almost remained the same until 2014, and then it has started to decline. Okay, so what we have now understood is the emissions are increasing, but emission intensity is sort of changing. It looks like declining. And what is the significance of emissions intensity? Why did we put our target in emissions intensity? We put our target in emissions intensity is, the reason is that our economic growth is not altered. The growth pathway is not altered by our decisions. Will it or will it not depends on how much investment from that GDP we are making in E and RE or other strategies to meet the challenge. Okay. So the emissions per unit of economic output is declining. Emissions are going up, but the emissions intensity is declining. So let's look at what are the factors that drive emission. So emissions go up, will definitely go up as economic activities increase. Economic activities, if the energy source continues to be fossil fuels, emissions will not go up as economic activities increase if we replace fossil fuels with renewable energy sources. But energy consumption will go up as economic activities will increase. Okay. So actually it should have been emissions intensity goes up as economic activities increase. Emissions will go up as long as we are not replacing fossil fuels, but emissions intensity will go up as economic activities increase. If they don't increase, then emissions will come down. I mean, so the total emissions will come down depending on what we are doing to our emissions intensity. Okay. So some of the emissions can be avoided by decreasing emission intensity. So what we are now interested in is to find out this decline is happening. What is driving this decline? So this decline could be because our fossil fuels are becoming less carbon intensive. So as I said, coal is more carbon intensive and natural gas is less carbon intensive. Both are fossil fuels. If I shift from coal to natural gas, then I'm shifting to a fossil fuel which is less carbon intensive. Now it can also change if we shift towards non-fossil energy sources, obviously. So nuclear and renewable and non-fossil energy sources, if we shift towards that, our emissions can decrease through decline in emission intensity. And finally, if we use less energy for the same output, then we are burning less fossil fuels, and that will also lead to emissions decline. But if you look at these two, these are basically changes in fuel mix, energy fuel mix. And this is energy efficiency. Not strictly speaking energy efficiency, but decline in energy intensity or change in energy intensity. So in addition to changes in fuel mix and energy efficiency, shift in economic structure also changes emission intensity. And we'll see how this is happening. So this is very famous KAA identity. This came in place in the 1990 IPCC report. Came in the highlight in the 1990 IPCC report, wherein carbon dioxide is written as an identity. Okay, so left hand side and right hand side both are carbon dioxide only, but it is written as an identity with multiplicative terms, and each of these terms is known as the KAA factors. What are these terms? P is the population, GDP per capita. Okay? This gives a sense of what is the overall income levels. E by GDP is the energy intensity. This is energy used, the total energy used, fossil, non-fossil, all energy, the primary energy which is used per unit of GDP. Now, FF is the fossil fuels, is the energy from fossil fuels, and E is the total energy. So what this term becomes is the fossil share. Then there are three types of fossil fuel, three fossil fuels we know, coal, oil, and natural gas. So I here is 3. So the share of each of the fossil fuel in the total fossil fuel energy supply is known as the fossil mix. And finally, carbon dioxide emitted by any one fossil fuel divided by the total energy from that fossil fuel. So this is known as the carbon dioxide intensity of a fossil fuel. So this value will be higher for coal and lower for natural gas, just to connect with what we talked about in the last slide. Now we can give them different, these different terms, different nomenclature. So G becomes per capita, EI becomes energy intensity, FS is fossil share, FM is fossil mix, and fossil carbon intensity is FI. Now see, this is from the supply side. Supply side meaning, what is the supply side meaning? What is the looking at the energy supply, looking at the emissions using energy sources entering into the economy. Okay, not in terms of what is getting consumed. Now, this is from the supply side. The other way of looking at carbon dioxide emissions is from the demand side. So carbon dioxide emissions can also be written as an identity using the energy consumed by each of the sector. So what's happening if you look at the energy flow? The energy sources enter into the economy. Okay, coal, oil, natural gas, renewable electricity, energy from renewable energy, electricity from renewable energy. Now, coal goes through this transformation process of electricity generation, and crude oil goes through the transformation or through refineries, and the petroleum products are produced. And natural gas does not have to go through transformation. So there is a transformation step in the middle. And finally, what are the energy, the secondary energy output? So electricity, oil products, diesel, petrol, then natural gas, all of this go to different sectors. Which sectors are there? You have residential, transport, industry, agriculture, service, commercial sector, and so on. So these are the final sectors. We can look at what is energy that is being supplied to the economy before the transformation. And we can also look at what is the energy consumed by different sectors. It gives us almost the same numbers when we look at emissions from the supply side or the demand side. So in IPCC terminologies, it is known as the reference approach and the sectoral approach. Now I can decompose, or I can see the effect of changes in carbon dioxide at the supply side also and at the demand side also. Okay. What is the benefit of looking at the supply side? What I see is how is renewable energy and energy intensity playing a role. What is the benefit of looking at the demand side? I can look at how uh, energy intensity is playing a role through technology and through changes in the economic structure. See, if we move towards services, our energy intensity will decline on its own. We don't have to use efficient technology. So energy efficiency is then not needed to reduce emissions. We can shift to services sector, use less energy and get more output. But we don't, that's not our aim. We are not going to meet our climate goals by changing the economic structure. We want to meet our climate goals by improving the technology which is used either in services sector or in the industrial sector. Okay? Now, this method of decomposing carbon dioxide from the demand side helps us to see that if there is a change in energy intensity, is it due to the economic structure? Is it due to shift towards services? Or is it because of improvement in technology in each of those sectors? There can be shift in the structure of the sector also. Now in manufacturing also I can shift more towards production of steel and iron and steel, which is more carbon intensive. So that's why I do not call this energy efficiency intent or energy efficiency here, because this is still sector energy intensity. Now I may not have that much time to go into the depth of each of these aspects, but what I will do is I will give you the references because these are from my recent work. So I'll give you the references and you can go in deeper into what they are, and you can always ask me questions about any one particular aspect that you're looking at. But let us very quickly look at how to estimate the effects of so these are all in multiplicative terms. Okay, and I want to arrive at, okay, so there has been a change in carbon dioxide emissions between two time periods. Okay, it is that change in carbon dioxide which I'm interested, because I want to bring that change to a smaller and a smaller value, because I want to minimize that change. I want to somehow bring it to a negative value. So that's my objective. Okay, so I want to bring my emissions to start declining. So this is the aggregate, and this is the change in aggregate. So delta CO2, which is difference of CO2 in time period t and CO2 in time in a base period, say year zero. Is there a way that I can look at these multiplicative terms in terms of their contribution in change in CO2 emissions in additive terms? Okay, so how do we estimate the effect? So the idea lies in your index number theory. Okay, one very simple way is you take a log, sorry, d won't be here. So you take log on both sides and differentiate, and you use the growth rates. So for example, if you just have a function xy and you want to see the change in that function, and you want to find out what is the contribution of changes in x and y in change in f, you can look at it this way. And when you divide it by ft on both sides, you see that the change in the percentage change in the aggregate is equal to the percentage change in the multiplicative terms. Of course there is a residual. Now this residual is higher for larger changes, and that's why people use perfect decomposition techniques such as Fisher index or log mean Divisier index. So what I did in my work in these two papers is I used log mean Divisier index, and in the first paper I did it on the primary energy supply, and I decomposed it into the KAA factors. And in the second paper, in the second conference paper, what I did was, this is work still in progress. So what I did in this is I look at the demand side and how economic structure and energy efficiency, energy intensity in sectors are contributing to changes in carbon dioxide emissions. So I will very quickly go through the results of these papers to give you a sense of what, from taking from what we saw as a method and what were the results. And please feel free to go deeper into this. So now these papers also have references to the literature where all of this comes from. So you can look at the literature to understand the different decomposition techniques and so on. So these are the factors in the KAA identity. If you remember, we talked about population, per capita income, energy intensity, fossil fuel share, fossil carbon intensity. So we see that emissions are rising, per capita income is rising, the population is also steadily rising. But what is declining is only energy intensity. So we saw that emission intensity decline graph. And now we can say that emission intensity is declining mainly due to decline in the energy intensity. What does it mean? That the fuel mix changes is not playing a role, meaning that shift to renewable energy is not seen. So all we see is that decline happening from late 90s, and then again during the economic crisis there was a change, and then it started declining again. And when we use the log mean VCR index approach to calculate the change in carbon dioxide due to different factors, we see that in the early years there were some changes in terms of the energy intensity was declining, but the economic growth was pushing the emissions up, but there was not significant change in the change in CO2 emissions. So the change in CO2 emissions remained the same. And so from around 2003 onwards, we see India's growth has changed substantively. And from 2005 to 10, we see that everything increased. So energy intensity also contributed to increase in emissions. But from 2010 onwards, energy intensity is contributing to a decline in emissions. Now, moving on to the demand side results, this was from a different paper, and hence the look is also very different. But you'll be able to get a sense now. I have looked at 3 sectors. Now, residential and transport I have not looked at because for them, the activity does not have an economic indicator. So for industry, services and agriculture, we can use GVA. But for transport and for residential, we don't have an equivalent economic indicator. But there are ways to do that as well, which I'm currently exploring. So what we see here is the economy structure. Economy structure did not play any role until 2010. So though industry was increasing, but agriculture share was declining. And we know that transformation took place, right? But as we see from 2010 onwards, the services sector increased and both industry and agriculture is declining. And hence the economy structure is also playing a role in that decline in energy intensity. So here we are seeing declines in energy intensity. We are trying to see where is this decline coming from? Is it from improvement in technology or is it from change in economy structure? So we see that economy structure is playing a role, and energy intensity is also playing a role in that decline in energy intensity. And CO2 intensity, as we saw in this as well, that your fuel mix and fuel intensity are not playing a significant role except in 2010 and 2000. Okay, so here. Yeah. All right. So this is about the decomposition results. Very quickly, we'll have the key takeaways. So index decomposition analysis we saw as a useful tool to measure the contributions of energy intensity and fuel mix in energy use and related emissions. So we were interested in figuring out how is energy efficiency and renewable energy doing to meet our climate goals. And with the index decomposition analysis, to some extent, we are able to figure that out. The problem is we cannot say which policy is causing this. So this is an aggregate change. This is an aggregate view. We will never be able to say which policy is doing how much to this decline. So that's a drawback of this method. So our clear finding is that India's emissions are increasing, but the emission intensity is declining. The decline in emission intensity is driven by the decline in energy intensity, and fuel mix does not have a role yet. And the decline in energy intensity is driven both by economic structure and energy intensity of production sectors. All right, so this is all that I had for the lecture, and I will stop here. I have indicated the references that you can go through, and I've also told that in those references are list of literature which is relevant to this area. And if there are any questions, then we can take that up in the live lecture time. Okay, thank you, and wish you good luck. Thanks.